Okay, guys. So today it marks the beginning of a webinar series organized by Ethereum Greece, focusing on layer 2 solutions and decentralized applications. We will be inviting key speakers, researchers, and engineers from the field to talk about the domains they know. Today with us, we have Luca Donnoh from L2BEAT, a Web3 researcher working on the risk framework from L2BEAT, amongst other things. The risk framework is the state of the art when it comes to assess the maturity of a layer 2 solution. Today, Lucas will speak to us, will introduce the layer 2 solutions, will speak on the rollup types and differences, and will give us a brief on the risk framework. And of course, we'll do a case study, which will focus on Arbitrum. Luca, thank you for joining us. The stage is yours.
Thank you. So yeah, first of all, thank you for having me, for inviting me. My name is Luca, and I am head of research at L2BEAT. As he said, what we do is analytics, but mostly risk assessments of these L2s. I'm going to explain what L2s are from first principles. I'm going to share my slides in a second. Yeah, we've been doing this for 4 or 5 years now. So at the very beginning, space, all things have happened. So let me get straight into it. I can guess my screen. Yes. Okay. So I hope you can see it. Okay. So for this presentation, what I assume that you already know is more or less what blockchains are. I will assume that you know what Ethereum is, more or less, like nothing in super detail, and a lot of what are these notifications? Everything right? Okay.
Yeah, just people joining. I'll take it.
Okay. Rough understanding of smart contracts, like the fact that Ethereum is like a programmable blockchain, like how this is different from Bitcoin, for example, where there are like you cannot do very complex stuff while you can do it on Ethereum because there are smart contracts, but not much else. Like I will try to explain everything else that has to do with L2s from first principles, as if you were to kind of come up yourself with the concept of or the implementation of the L2s. So the first realization that we need is that there is no single world computer in the space, in the blockchain space, right? A lot of them like try to think of themselves as if they are the one blockchain, like the top, or like the blockchain that everyone should use. But in reality, there are thousands of them. Here I'm just like showing the top ones, but there are a lot of them. A lot of them are different, very different. Some of them are more similar, but are like managed by different entities. But in any case, what I'm trying to say is all these blockchains kind of have different trade-offs. They have different styles, different guarantees that they give you. Some of them are more decentralized, some of them are faster, some of them are private, some of them are maybe managed by some entity that you might like or not like. In any case, like users might have different preferences when choosing a blockchain. And this is also kind of a struggle for applications too. What happens today is any application that pops up tries to support as many blockchains as possible, right? Because they don't know, like there's no clear winner. They try to support them all, and this is kind of a problem because it creates some fragmentation and liquidity and stuff. So what happens in practice is that everyone tries to build bridges to all the other ecosystems, right? So for example, people on Solana might tell you, we are the fastest blockchain or whatever. So all these tokens that you can have on all the other chains, is better if you bridge them to our ecosystem, because our ecosystem is the best in terms of, I don't know, speed or whatever, right? Some other, they could tell you, we're the most secure, we're the most decentralized, so your assets are the safest in our ecosystem, right? So there is also this kind of incentive to also take stuff from the other blockchains to bring into your own. And this has created a lot of bridges across all these ecosystems, right? Here, like, I tried to picture these bridges, but in reality, there are even more, right? Like, you can imagine a full graph, something like this. This is kind of a visualization that we have internally at L2BEAT that shows every line, is a connection, and there are these flows of value that moves between chains. And there are a lot of chains, as I said, right? So a lot of things today in the blockchain space have to do with bridges. And there are many ways to build a bridge, right? You can build very secure bridges, like this one is Ponte di Tiberio in Rimini. This is a bridge like in my hometown in Italy that has over 2,000 years and it still stands. Like, people are still using it, cars and people. And there are other bridges that are terrible. There's like a newer one in Genoa that collapsed a few years back. People died in this because of this bridge. And what I'm trying to say is, don't think that this is different in the blockchain space. People also sometimes do die because of losing money, and we should take like these things very seriously, in my opinion, right? So and yeah, so as I said, I don't want to get too dark, but there are many ways you can build a bridge, right? So I want to take a step back and pause for a moment, because I want you to think kind of deeply about this problem. The problem that we have at our hands is, I have an asset on one chain, let's say Ethereum on the left, and I want to bridge this asset to another blockchain. Let's say Avalanche. It doesn't matter, if you don't know what Avalanche is, just a random example. And I want to bridge this token, which is WETH, which again, you can think about this token about like as a random token. And like, how would you even start? Like, I have this asset in my account on Ethereum, and I need somehow to send a transaction that says, okay, I want this asset to be on this other blockchain. But the problem is, this other blockchain is a completely separate thing, right? Like, it's its own ecosystem, its own like validator set, its own network, right? It doesn't have native visibility of Ethereum. So how do you even start? This is the message I want to get to you, is that this is a genuinely difficult problem. This is like saying, I want to create, like, I want to be able to create tweets on Twitter, on X, from Telegram, right? These are two completely different social medias, social platforms, right? Social networks. And you might start to think, how to solve this. Like, maybe you need a third service that kind of reads stuff from Telegram, right? And you need to give access to your Twitter account to this service. It needs to be able to post tweets, right? And what if this service is compromised? It might tweet for you, even though you're not sending messages on Telegram, or it might read your Telegram stuff, right? It's very difficult to make two things communicate when they do not do this natively. So there is a bridge between Ethereum and Avalanche that tries to, implement this feature. And the way that this bridge is built by Avalanche itself, by the way. And how do they solve this feature, this problem? They solve it with a trusted entity. So they put this actor in the middle, which is controlled by Avalanche. Like literally, this is an account that has a private key like any other account that is controlled by someone at Avalanche. And to bridge your funds from Ethereum, what happens is that you send those funds to this person on Ethereum, right? Like it's a simple transfer. It's not even a smart contract. It's just a simple EOA, they're called, which are simple accounts with no code. Send funds on Ethereum to this address, and this address on Avalanche is supposed to mint a token that represents the token that you send to him on Ethereum. So in this example, if you send to this actor wrapped ETH, he will like custody this wrapped ETH, like the original token, in its own account, and this actor will create a representation asset on Avalanche. And if you go to CoinGecko, which is a website that has a lot of collects a lot of tokens and prices, they even call it a different name. They call it Avalanche Bridged WE with Avalanche between braces. So, and this to say is that you're not actually bridging the token, right? Like it's not the same thing. What you do in practice in this example is that you send the original token to someone, and this someone sends you a token that he creates. And the promise is, if you give this token back, this actor will like unlock the tokens that he keeps and give it back to you, right? And like in technical terms, like in economy and finance, this is called an IOU. Like this token that you get on Avalanche is called an IOU, which is basically something that represents some debt, right? So since you gave these tokens to this actor has some debt towards you, and this debt is represented as this representation token. But again, you need to trust this actor that, for example, it doesn't go away with the token that you gave him, because what he could do is mint the token and just run away with the original ones, and then these tokens would not be backed anymore, would be of zero value. Another thing that you can do is just mint tokens out of nothing, right? Because he has the power to do so. He's the source of truth on whether people have sent him the assets or not. So he could overmint, he could just get away with tokens and so forth. This entity is fully trusted. And this is the address on Ethereum that holds these tokens. It is tagged as Avalanche Bridge because it is the Avalanche Bridge. And as you can see, for this wrapped Ether, it has like 35, almost 36 millions of dollars of this token. And again, this actor could just run away with these tokens, or if it gets malicious or if it's compromised. Because as I said, it's a simple private key, and as a total, it has 134 and something millions of dollars in custody. And the fact that this actor can be compromised is not just theoretical. This happens, and there are many, many examples. This has happened in 2023. This is multi-chain, and as the name suggests, this was a bridge, a cross-chain bridge protocol that was trying to bridge tokens across chains, and this was controlled by some trusted entity, the same way as Avalanche. These keys got compromised. I'm not sure whether it was compromised by an external party or it was like the team itself that decided to steal the funds. But yeah, like the CEO was arrested by the Chinese police, like something happened. And this is another example, Axie Infinity. This was one of the biggest hacks in blockchains ever. This is $5.5 billion being stolen because of a similar exploit. Some key was compromised. This happened last week, actually, 3-4 days ago, where like a stable coin, like a token that had an actor that could mint, that could create this token, was compromised. Again, this is not clear whether it was an insider or some external actor that got access to the key. Okay, I'll give you one more, which is this other blockchain, which had a bridge to Ethereum with some validators. It was not just one actor, it was a few. But in any case, a majority of them, since there was a quorum, something like more similar to multisig, a quorum was compromised and funds in the bridge that were locked in the bridge were stolen. So this was last year. And these things like happen all the time. Keys get compromised. So this is not like the best model that we could have in blockchains when we want to bridge funds, right? So another case that I want to show you is between Ethereum and Near. Near is this other blockchain that is more or less completely different than Ethereum. It has a different execution environment, different language to write smart contracts, or whatever. It has smart contracts as Ethereum, and because of this, you can build a bridge if you want to, right? They wanted to do something that is better than what Avalanche has, and the realization here is that blockchains have validators, right? They have a validator set, which means that everything that happens on Ethereum, for example, is checked and signed by its validator set, right? So, for example, if I say I'm on Ethereum and I want to bridge my funds to Near blockchain, when I include this transaction on the blockchain, the validator set will include it and sign it. And the validator set on Ethereum is very big. There are almost 1 million validators, right? And for something to be included, to be finalized, you need a signature from over 2/3 of these 1 million validators, which is a lot, right? Over 600,000 validators. On Near, there are less validators, but it's very similar. There are a few hundreds, I think, maybe 200-300. And you still need, you know, a majority of this to sign something. So one idea is, what if we use these consensus signatures for the source of truth? Like, instead of introducing a third party, we kind of have already some parties that can attest that something happened on this blockchain with a signature, which is not a third party, it's a first party, right? Because it's a validator. And if you can manage to verify Ethereum consensus on Near and back, you can have a two-way bridge that only relies on the honesty of these supermajority of validators. And since some blockchains are very big, like Ethereum, but also Near is quite big of a blockchain, this is pretty secure. Like, it's very difficult for, or like, this is an assumption, at least, right? It is kind of unlikely that either all the validators get compromised because there are a lot of them, or they just become straight up malicious, right? There is an actual implementation of this that is live. You can use it. It's called the Rainbow Bridge between Ethereum and Near. And if you look at the docs, this is like a very old bridge. Has been live for, I think, 4 years, maybe more. And if you go to their docs, they say, we built a bridge called Rainbow Bridge to connect Ethereum and Near blockchains, and we created the lowest possible trust level one can have for an interoperability solution. And this was true in the sense that this is way, way better than what was before, like the Avalanche model, where you have just one single trusted party. It is not the lowest possible trust level though, and I'm going to explain why. But still, this is pretty good. Like if you see a high client bridge between two chains, and these two chains are big enough so that you can kind of trust the validator set, this is a pretty good bridge. It's something that I would use personally. If you take this concept of these consensus, these bridges that verify consensus signatures to the extreme, you get something like Cosmos. So Cosmos is this ecosystem of blockchains that are more or less similar, or at least they share some APIs or some interface to communicate with each other. And what happens here is that each one of them has its own validator set, and there is a standard protocol to verify signatures from one chain to another chain. And in this way, it kind of gets easy in terms of implementation to bridge funds between one another. There is this website that is called Map of Zones that shows all the blockchains in the Cosmos ecosystem and the funds that are bridged between one another. And, you know, the bridge that was built between Ethereum and Near, it's custom. It's quite custom. And it's kind of difficult to get this right because the consensus set, consensus algorithm was not designed to be like verified on all the blockchains. So sometimes it gets expensive, for example. But Cosmos, tried to design the blockchain itself around the concept of, it should be easy to verify consensus signature from this one chain to another chain to make it easy to bridge funds. And this has been live in production for many years already. And the problem is that this model can fail as well. So as I said, you're trusting that the supermajority of these validators are honest. And if someone wants to bridge some funds, actually the validator will sign something that attests that this is actually the case, right? But if a validator set is malicious, they could sign whatever they want. They could sign, for example, that John wants to bridge 1 trillion tokens to Near. And Near, the only thing that they can do is to verify the signature and just use them as a source of truth. So if Ethereum says this guy wants to bridge 1 trillion tokens, Near will say, yes, I accept it. Again, this scenario is unlikely for big chains, in my opinion. It is unlikely that Ethereum, with its own almost 1 million validators, will manage to sign something that is invalid. Also because all these validators have a stake, right? And if they do something malicious, they sign something that is false. You can see it. Like it is a fault that we say is attributable. There is your signature, the signature that is associated to the validator. The validator has some stake. And if we notice that some validator misbehaves, we can take the stake away. We say we can slash those validators, right? So, for example, let's say the economic security, which is the total sum of the staked tokens of a validator set, is $1 billion. You need like $600 million of dollars to be malicious to sign something that is invalid. But if this happens, we will be able to slash those tokens. So we say the Ethereum network provides $600 million of economic security in the sense of it is only profitable and rational for these actors to commit this fraud only if they can get more than $600 million of value out of it when doing so, right? Which is a very high ceiling. There are also like other reasons not to do so because, for example, you might go to jail. But whatever, these chains have some economic security because we know that if they commit something wrong, we can slash those value and those tokens. So they will lose some some money if they do so. But again, if this happens, we can slash those tokens after the fact, but if near accepts the signatures of this malicious validator set, there's nothing that can resolve this. Like the bridge is screwed. It could be that this 1 trillion tokens gets minted at near. And even though you slash those tokens, this is not reversible. Once you bridge, you've bridged, right? Near will have no concept of a malicious signature because this is the source of truth. A signature is a signature. Whatever it says, it is correct. And so again, while this is unlikely for big chains, in the Cosmos ecosystem, I tried to ask Claude to give me like the blockchains in the Cosmos ecosystem that have the lowest economic security. And as you can see, like in the last column, a lot of them have less than $100,000 of economic security, which means that, for example, if you take Comdex, which is the worst one, there are only $8,000 of economic security. One can simply buy this random CMDX token and take over the validator set and sign something that is malicious. And if there is a bridge on some other blockchain that accepts tokens from this Comdex chain, you can like compromise it. You can mint whatever tokens you want. You can steal funds and so on, right? So if the economic security of your chain is very low, it is actually feasible, like very feasible, to compromise this chain. Okay? So while you might think that this is unlikely that the bridge, the rainbow bridge that is between Ethereum and Near gets compromised, something like a bridge between Comdex and Planck, which are the like worst two in this table, is actually quite possible, quite realistic. If this doesn't happen, it's probably because there is not enough value to steal. But we actually have North Korea doing hacks in blockchains. So if there is actually something like this that is exploitable and is profitable to exploit, it will be exploited. So this is a problem, right? And the source of problem of this is that its own blockchain needs to build its own validator set. And if you have thousands of blockchains, it's very difficult that all of them will have millions, like hundreds of millions of dollars of economic security. It's very likely that if you have a lot of blockchains, there will be a lot of them that will have very low economic security. Like this is almost inevitable. So I want to for a moment explain what is the difference between a light client or a light node and a full node. So if you want to run a node for any blockchain, you have these two options. One is a light client and one is a full node. A light client, as the name says, is lighter than a full node because the only thing that it does is that it trusts the validators. If the validators say that something happened, then you will just trust it. You just follow the chain that is signed by the validators. You don't get the transactions yourself. You don't compute the results of these transactions. If you don't compute the results, it means that you also don't need the state of the blockchains, which is sometimes quite big. And again, if the validators are malicious, you can be compromised. And this is a light client. And this is why we call this model light client bridge. This takes the name of a light client bridge because it has the same security of a light node. It just trusts the validators. On the other side, there is a full node security, which is you don't even trust the validators themselves. So when a block has some transactions and you want to know what is the result of these transactions in a block, you will take the block, you will take the transactions, you will have a state that you maintain yourself in your node, locally, and you will compute these transactions. You will execute them, you will run the smart contracts that they call, and you will save the new state, right? So if I make a transfer, and this transfer is in a block, a full node will take the transaction with the transfer, it will validate the signature of this transaction, and will like check that I have enough balance to transfer the amount that I want to transfer, and so on. So even if all the validators in the network are malicious, they cannot compromise a full node, because a full node will check everything by itself. There is no way to compromise a full node, even if 100% of the validators are compromised. So we can kind of get the idea that something that is better than a light client bridge, than a light bridge, is something that gets closer to a full node, where you actually check everything. So there are two dream features for a bridge. And by the way, if there are like questions, please someone shout at me so I can like stop.
Yeah, Luca, there is a question in the chat.
Yeah, please tell me, because I cannot see the chat.
Yeah, let me find how to open it. I don't see the chat, Anastasis. Can you read the question? For some reason, I can't see.
Yeah, for sure. George is asking, what is the point of a light client if he doesn't validate?
The point of a light client is that it's super light, as the name suggests, in the sense of like a full node requires, for example, in Ethereum, a full node, which I run, at home myself, requires 4 terabytes of NVMe disk, 4 terabytes, and it requires some bandwidth, right? And you need to have, processing capacity, like a CPU that can sustain the load, right? So what happens is that for my node, I have a full computer, like desktop computer, to run my node. And I need these 4 terabytes. If you're a light client, since you do not execute the transactions, you don't need these 4 terabytes. So it is possible to run a light client, for example, in a browser of a laptop, very easily. Or you can run it on your phone even. There are people running light clients on a Raspberry. There are people running light clients like on anything. It's like similar to Doom. You can run a light client on your watch if you want to. But the thing is that you get degraded security, because again, you're trusting the validators to say something that is true. But again, for some blockchain, this is pretty good. It's kind of unlikely that the validators will lie to you if the chain is big, but this might happen. And if this is not good enough for you, then you should run a full node. This is like the difference. It's a trade-off between security and hardware requirements to run the node.
Luca, he continues the question and is the following: but what does he offer to the network? That's the part I didn't get.
Sorry, can you repeat?
Yes, he asks, what does he offer to the network, the light client?
Oh, yeah. So it is important not to confuse nodes with validators, right? A validator is something that participates in consensus. And participating in consensus mainly means deciding what is the order of blocks. So a block arrives to you, you sign this block, and then you say to all the others, look, I saw this block before this other one, for example. Or like, this is the block that comes after this other one, and I checked like all the chain of blocks that comes before it, right? But you don't need to be a validator to run a node. There are nodes that are not validators, and the reason why you want to run a node that is not a validator, which again doesn't have a stake, does not earn rewards, is because you want to simply read the chain. You want to know what happens. You want to send transactions, and you want to know, for example, if someone sends you a token, you want to know whether this actually happened, right? What is the amount and so on. If you don't run your node, for example, you just have a wallet, like as an extension in your browser, what happens is that you connect to an RPC, an external RPC, which means you're not connecting to your node, but you're connecting to, for example, Alchemy or Infura, or with these RPC services that will give you the information that you request. But the thing is that you are fully trusting these centralized entities to give you the correct view of the chain. Like, for example, if I tell you I will send you 1 Bitcoin and I'm using an external RPC for this, or like 1 Ether, and I'm using an external RPC, and this RPC is compromised, it might tell you that this actually happened while it didn't. So you might give me a service, a house or a car, even though I didn't actually send these funds. So the only way not to rely on these third-party RPC providers that usually come with the wallets in your browser extension or on your phone is to run your own node. And in some wallets, what you can do is to change this RPC. Instead of saying the RPC that I'm trusting is, I don't know, rpc.infura.com, I use localhost at this port on my computer, if that makes sense. Any other question?
Yes, there is a new one, and is the following: why to use bridge tokens and not trade twice to do a transaction on a different chain? What's the usability?
Like, why would you bridge a token to a different chain? Is that the question?
Something like this. So, Vasilis, if you want to use Ethereum on Near, for example, you should use a bridge token because Ethereum doesn't exist natively on the other network. Does it respond to your question?
I mean, the reason is that simply, there might be some applications that you want to use on Near that all exist on Near and not on Ethereum, right? So if you want to, for example, you have perpetuals DEX that you like, or some margin trading with an application that you like on Near, but you want to trade ETH token, then you need to bridge somehow. And goes the other way around. If you ever use Hyperliquid, there are lots of assets on Hyperliquid, so you kind of need to bridge something. Okay, I will continue because I have quite some slides.
Yes. Go ahead.
So as I said, the dream feature for a bridge is, by the way, I will stay a bit later to answer the other questions, so don't worry. So the dream features for a bridge is to have something that is closer to a full node security, where you don't even need to trust the validators of these other networks because you check everything. So this is the second feature, which I write. The bridge is not compromised even if this single validator set is 100% compromised, so you get full node level security. And the other dream feature is that multiple chains can share the same validator set, which is the same economic security. And this is kind of crazy, right? If you think about it, the first one. Because usually when we think about different blockchains, we think about each one of them having their own validator set, right? It's this model. All these blockchains have its own validator set, and some of them might have low economic security. Turns out there is actually a way to have multiple blockchains that share the same validator set and the same economic security, even though they're completely different chains. They can have their own custom virtual machines, their own custom smart contract environments. They can even not have smart contracts if you want to. but they reuse the same exact validator set and have the same exact economic security, which is kind of crazy. And I want to start with this. Like, I want to give you the intuition how this is possible. So what happens in a blockchain is that, like, what does a validator set do in the first place? And I kind of suggested this already. What a consensus algorithm does with some validators is to order transaction. The problem, like if you read, for example, the Bitcoin white paper, the whole deal with blockchains is like, how can we get global consensus? Which means, how can we make a lot of different people agree that these things have happened in this order, in this exact order. And ordering is the tricky part. And ordering is all that consensus algorithms are about. And this is all that blockchains are about. Because validity is not a difficult problem. Validity is easy. Like, if you have the inputs of a program and you have the program, it's easy for you to check whether the output is correct, because you simply recalculate, you execute the program yourself, right? So validity of transactions, it's a super simple, trivial problem. The difficult part is, how can we make everyone agree on what is the ordering of these inputs, of these transactions? The transactions in a blockchain are the inputs, right, of this transition. And you want to have a big validator set, and you want to have a lot of economic security, so that once the network agrees that something is put in this order, it cannot like change its mind easily, right? It cannot reorg. In Bitcoin, we call about reorgs. Also in Ethereum, we can have reorgs. Some blockchains have the concept of finality, which means that when enough people, enough validators vote for a transaction, it is considered final. Even final transactions can be reorged, actually, if there is a consensus failure. But in any case, what I'm trying to say, blockchains are about ordering. And users send transactions to this chain. The chain orders based on, time of arrival, more or less. And that's it. And this is how you get, economic security out of a blockchain. The thing is that you can use the same exact mechanism to, like, instead of being a user, you can be like a separate blockchain. And it is this Arbitrum logo, which is, again, a separate blockchain from Ethereum. If you do the same as a user and you send transactions to Ethereum, Ethereum will order these transactions for you. Like, you don't need to have your own validator set that orders transactions like separately. You can reuse another blockchain to order the transaction of your blockchains, And this is kind of crazy. It's super cool that this works in practice. What is the difference between these two scenarios, the user and the other blockchain, is that if I'm a user and I'm sending an Ethereum transaction to Ethereum, this transaction will get executed. If I'm an L2, in this case, if I am a separate blockchain that sends transactions to Ethereum, I don't care about, I don't want them to be executed on Ethereum. The only thing that I want is, I want Ethereum to define an ordering, to finalize this ordering with the economic security that Ethereum has. And then this other blockchain, like Arbitrum in this case, will take care of deciding how to interpret these transactions, because it could even have different transaction formats. They could be like completely different. But this concerns Arbitrum. It doesn't concern Ethereum. And this is why like the blockchains that do this are called L2s, for this reason, that they L2s compared to an L1. L1 is the like base blockchain that has the big validator set and orders transactions. The L2 is another blockchain that sends transactions to the first one, but are not executed. I hear maybe a question.
Yeah, George has raised his hand. George, please go ahead.
Sorry, I don't mean to interrupt. Just I'm raising my hand to keep track of the queue if we ever reach the question part. So please go on when we can have it at the end.
Okay, that sounds good. So Ethereum introduced the concept of another blockchain sending transactions that are not executed on Ethereum natively. There is this feature that was introduced with EIP 4844, which are called blob transactions, which is basically anyone can just send a piece of data that is not interpreted by the Ethereum virtual machine, where Ethereum just orders this data, but again, it does not execute it, right? And L2s make use of these features that Ethereum natively supports. So the first feature is done. This is how you get multiple chain that can share the same validator set and the same economic security. You basically allow them to post transactions to this other blockchain. The difficult part is how to get full node level security. This is the generally difficult part that was discovered 4 or 5 years ago, and it's generally complicated. So now let's go back to this example. I am a user on Ethereum. I want to breach my funds on Arbitrum, and as I said, Arbitrum has this property that Arbitrum transactions are posted to Ethereum. So if you want to derive what is the state of the Arbitrum chain, you need to read what is on Ethereum. So another way to say this is that Arbitrum natively reads Ethereum, because Arbitrum needs to read Ethereum to know the ordering of its transactions. So Arbitrum natively integrates Ethereum in a way, right? In my old example, it's like saying Twitter natively reads from Telegram directly, right? So sending funds from Ethereum to Arbitrum is completely trivial. It's completely a trivial problem, because if Arbitrum can read Ethereum natively, it can read that there is this user that wants to breach funds, and there is no way to compromise this, right? I want to breach my funds from Ethereum. I just say, I send a transaction that says, yes, I want to breach these funds. I lock those funds on Ethereum in a smart contract usually, and then Arbitrum itself will mint these tokens. And anyone that is running an Ethereum node can see that minting these tokens on Arbitrum is correct, because all these nodes are also natively validating Ethereum at the same time. So it's kind of, Arbitrum is like a superset of Ethereum in a way, right? So sending funds, if you have a blockchain that natively reads another blockchain, sending funds to it, it's trivial. And this is why, on Avalanche, for example, the example that I made before was tricky, because Avalanche has no way to natively read Ethereum. So you kind of need someone to tell to Avalanche that something happened on Ethereum. So going back to Ethereum and Arbitrum, the difficult part is how do you get back? What if I want to, I'm on Arbitrum and I want to breach my funds on Ethereum? And while Arbitrum natively reads Ethereum, Ethereum has no idea that Arbitrum exists even. Ethereum can see that Arbitrum is posting transactions, that is true, but it doesn't know how to execute them, how to interpret them, because it said Arbitrum could have a completely different execution environment. And it does. Arbitrum actually has has like Ethereum execution environment, but they also implement an additional execution environment that Ethereum doesn't have. So how can Ethereum know that something happened on Arbitrum? How can Ethereum read Arbitrum? And this is, if you solve this problem, this is how you get something that is more secure than a likely bridge, right? One way that you could go about this is like, okay, Arbitrum can have its own like validator set, and then you trust Arbitrum validator set. But like, as we said, in principle, we don't even want to have a validator set in the first place. Like Arbitrum in principle doesn't need a validator set because it uses the one from Ethereum, right? But ordering is not enough. You also need to know about the result of this transaction, the outputs, how to execute this transaction. So option one is like, you take the transactions that are on Arbitrum and you re-execute if they're valid. So for example, there is a user that wants to bridge from Arbitrum to Ethereum. You need to check, for example, if this user has enough balance to even start this bridge transaction. You might think that you can re-execute all the transaction from Arbitrum to Ethereum, but in practice, this is not feasible. You cannot like re-execute on Ethereum all the transactions from all the L2s. Usually these L2s go much faster. They have much higher throughput, transactions per second than Ethereum. So this is not an option in practice. And also, Ethereum execution environment is different than the one from Ethereum. So this is not, you cannot do this, right? This is what a full node would do, trivially, as I said before. It just executes a transaction, but it's not possible. The one option that is actually feasible is to use ZK proofs. And the best description of ZK proofs is like cryptographic magic. I don't have time to explain how ZK proofs work. I think it might be a good opportunity to invite someone at ETH Greece that can explain like some intuitions about ZK proofs. But what I want to tell you is that there is some new cryptography that exists that was made practical only 4 or 5 years ago, basically. The theory is maybe has 10, 15 years. So it's very new. The girl, the lady that invented this cryptography, she's called Goldwasser. She won the Turing Award, which is basically the Nobel Prize for computer science because of this. But basically, a ZK proof is a short string, a short amount of bytes that will convince you that a result is correct about some computation without having you to re-execute all the computation itself. And verifying that this proof is correct is super, super cheap and super, super easy. How to compute this proof is harder, but whatever. Like the message is there's this new cryptographic primitive, which is called the ZK proof, that is very similar to magic, in my opinion. Like it's incredible that this thing exists. I will try to give you an intuition in the next slide about this, but it's a super interesting topic. One of the reasons I started like working at blockchain in the first place. The third option is to send a result without any proof that this result is correct, but you design some mechanism so that if this result is wrong, it's easy to prove that it is wrong. So the intuition is for ZK proofs is solving, I use Sudoku puzzles here. Solving a Sudoku puzzle is difficult. It takes a lot of time. If you have done some computational complexity in like computer science, or like theoretical computer science, is an NP-complete problem. It's difficult computationally, but verifying that a solution is correct to a Sudoku puzzle is trivial. So there is this asymmetry between like executing a problem, like resolving the problem, and verifying that a solution is correct. The third case, which is, you send something with no proof, but you can prove that this is wrong, is like I don't even have, let's say, computational capacity to check a solution entirely. But if someone points me to a couple of cells in this Sudoku puzzle, and they show me that, for example, they're the same number in the same row, I can immediately tell, just by reading 2 cells, that this solution is wrong. So this is the rough intuition. But again, this topic is super interesting, and I will suggest you to read about it. If you go to L2BEAT, L2BEAT.com, which is the website that we maintain, we explain in detail how this state validation mechanism is done for Arbitrum and for a lot of other chains. I don't have time to go over this. I love this topic, to be honest. I have like a super long article that explains how this works. So again, if you go to L2BEAT.com website, you will be able to more or less understand how this topic works. I know that it's kind of frustrating that I'm not explaining this, because this is the whole deal about L2s. But yeah, like just the messages, this is super cool, and you should look into it. So the way that you communicate back is either with ZK proofs or what we call fraud proofs. So if something is wrong, you probably is wrong. This is our website. Arbitrum is like the biggest chain, the biggest L2 that is out there. And there are a lot of them. We assess and look into the implementation of all these blockchains and how they work and how they implement the bridge mechanism. And since the technology is very new, because as I said, this is something that was made feasible only a few years back, some of them are not like fully complete or are so complicated that you need to have some like, you still need to have some centralized actor that looks after it. So we kind of, with this website, what we try to do is kind of try to assess the decentralization, like how much secure or decentralized these projects are. And we do this in 2 ways. One is what we call the risk rosette or the risk pizza, which is like these colored slices that you see on the left, and then the stage. And I will go like briefly on how these slices are assigned to Arbitrum. So there are 5 slices. We assign one of 3 colors, which can be green, yellow, and red, based on how good these things are. And one of these slices is state validation. So Arbitrum uses fraud proofs. It doesn't use ZK. It does, sorry, I had a call. Put on do not disturb. Sorry, yeah. So use fraud proof. This state validation mechanism is permissionless. Anyone can like use it. Anyone can like state that there is a fraud happening. So this is green for us. Another one is proposer failure, which is like again more or less related to who can do this, who can like participate in the bridge mechanism. In Arbitrum, anyone can do it. So this is green. Data availability is about where the data is posted. So as I said, the idea is that you can reuse another chain consensus if you post data to it. And again, I cannot go into the details, but there are many ways to do it. Some of them are good ways. Some of them are more trusted ways. So for example, some chains post the full transaction data, so you can have like all the data that you need to reconstruct Arbitrum state. Some of them only post like hashes, for example, instead of the full data. So even if you see the hash, if you don't have the like original data behind this hash, you cannot really reconstruct anything. So these protocols might be yellow or red, depending on some details. But Arbitrum posts the full data, so it's green. Sequencer failure is like, how do you get your transaction in? And the way that Arbitrum works is that if you post your transaction on Ethereum, then there is a guarantee that this transaction will also appear on Arbitrum. So the only way for Arbitrum to censor you is like if Ethereum itself censors you. And we call this mechanism a forced transaction mechanism because yeah, like you get the same censorship resistance guarantees of Ethereum, which is the best. A lot of other L2s don't have this mechanism, so this slice will be yellow, red. The exit window is the most complicated one to kind of understand and assess, which is the protocol Arbitrum is upgradable. The contracts can be modified by governance or by a security council, which is a multi-sig, more or less. But these upgrades have a delay, so they don't apply immediately. And this is helpful because if there is an upgrade that is potentially malicious or you disagree with this upgrade, you can decide to exit. This is why we call it an exit window. This is like the amount of days that the protocol gives you if you disagree with an upgrade for you to exit. This is the exit window that only applies for the DAO, which is like a decentralized organization that governs the Arbitrum protocol. We make an exception for security councils. Security councils are these, as I said, multi-sigs that are kind of big endeavors that are there. Like there are different entities behind these multi-sigs, like reputable and whatever entities that can also upgrade the system with no delay, which is a problem. This is a security concern. Like if the security council is compromised, in Arbitrum, I think it's 10 of 12, or sorry, a 9 out of 12, maybe. Then your funds can be compromised, which is a problem. That's why we show it as a red warning. But all these slices are independent. So you can have one slice that is green and one slice that is red, right? The problem is if you have, for example, a simple single actor that can upgrade a protocol and can change the rules and like steal the funds immediately. So if this slice is red, for example, do even the other slices give you any security? And you might say, no, they don't give you any security, because if they can change the rule, like even if they have these prop proofs, zk proofs, whatever protocol to make sure that all the transactions are validated, they can just change the rules out of nothing. Then they're not providing any value, right? So we have this other assessment, which we call the stage. We have 3 stages, stage 0, 1, and 2. And basically what the stage framework does is we take all these risks all together, and we try to see, like as a whole, whether the protocol is decentralized enough or not. Arbitrum stage 1, which is something in the middle between stage 0, stage 2. Stage 0 is like you're completely decentralized, you completely trust some actors. Stage 2 is there is no centralized actor that can drag you. Stage 1 is something in the middle, which I don't have much time to go over the details, also because I'm over the hour. But you can find all this information on the website. If you go back to this page, you can see there are some stage 1 blockchains. There are a lot of stage 0 blockchains, which is kind of bad. So Arbitrum is kind of among the good ones. But there are not many stage 2 ones, which is a bit sad. But the reason why this is the case is because the tech is too new to just run independently without supervision. Like all these teams don't feel comfortable enough to full decentralize yet, but ideally, they're working towards this thing. And if you go to our website, there is a lot of information. So you can read how all the upgrades work. We have full diagrams, how the operators work, all the permissioned actors in the network, like with all the addresses and description and what they can do. We provide like smart contract diagrams if you want to read about it. If you're like a visual learner, we also have this other page that is interactive. Like if you click on this go to Disco button on the page, it goes to this other page, which has each smart contract is like a box. You can move the box. They get highlighted. You can change colors. It's very like friendly in exploring how a system works. We assess like all these proof systems of these protocols in details. This is a Ziki catalog. It assesses all the technology that is used, like Ziki proofs that are used by these protocols, detailed pages on like, everything that you can know. And yes, this is all I had. And thank you.
Thank you, Luca. Thank you, Luca, for the great presentation. I have questions, but let's start first with our audience. Congratulations from me. George, let's go. You go first.
Okay. Thanks for the presentation. The camera is speaking. Thanks for the presentation. Really interesting. And thanks for your time. I would like to ask you a little bit about what about the incentives and the sequencing of such system. Like most of the, to my knowledge, most of the L2s or even like different L1s have different like sequencing logic, and most of them have like a centralized sequencer which they use to extract profits as well. And especially if we have like transactions that migrate funds from one L1 to another L1, and they're somehow connected with some Oracle stablecoin, they would cause like a brief imbalance on the price that would end in a MEV opportunity. How could this be handled? Like, what are your thoughts on this? Like this conflict of incentives between different L1s, which are basically a competitor.
Yes. So, okay. So I feel like there are two things. One is like how sequencing works on an L2, and I will take Arbitrum as an example. So as I said before, the cool thing about an L2 is that you don't need to have your own consensus set. And consensus does two things, actually. One is, as I said, ordering transaction. The other thing, and as I said, if you send your transaction to another blockchain, you can just reuse whatever ordering this other blockchain uses. So this is the first reason for a blockchain to have a decentralized validator set. The other one that they didn't talk about is censorship resistance. So you want to have many different actors because you want to have some guarantee that some of them, maybe not all, but at least some portion of them will accept your transaction and not censor you, right? And since for an L2, there is no need to like order transactions, what L2s do in practice is that they have no decentralized validator set at all. And so the question is, how do you guarantee censorship resistance in this case? And the way that it works is that you need to implement some gadget on top of your blockchain that allows users to force transactions from your L1, like from, in this case, Ethereum. And Arbitrum implements a forced transaction mechanism. It's like, as I said, I don't have time, unfortunately, to go over the details. But in the screenshot, I have this section, which is called section 15, which is called sequencing, and subtitled buffered for forced transactions, which explain more or less how this works. It's like a short paragraph. There is also a link to Arbitrum documentation. But basically, the idea is if you solve ordering and if you solve censorship by other means, you don't need to have your own decentralized validator set. So in practice, what Arbitrum has is like one single operator that decides, that does the sequencing of transactions. But the thing is, even if this single sequencer gets malicious and starts to censor you, you can bypass the centralized sequencer censorship by using this forced transaction mechanism. So this is why we say this is kind of tolerated, because there are ways to go around it. Can the centralized, what is the most damage that this Arbitrum centralized sequencer can do is like, yes, it can try to reorder transactions or like do some stuff to extract profit in the worst way possible. And yes, this is a risk that exists in practice. But again, the damage is limited because there is always a way for you to bypass it. And what is the incentive for decentralized? I think you also asked. The incentive for the centralized sequencer is that it gets the transaction fees. So it gets a profit. What is the advantage of like connecting to another chain? It's just because, like in practice, the more connected you are to other ecosystems, the more users you can get, simply. It's just better to try to gather everyone to your blockchain, to your ecosystem. So that's why everyone is trying to build bridges to all the other ecosystems.
Thank you. Any other question, guys? Okay, then I will go with mine. Before I start the question, guys, on Monday, we will cover briefly the third group mechanisms of Arbitrum, and we will talk also about the risks, about what sequencer can do and cannot do. So I jump into my question, Luca, and is the following. So when we are thinking of rollups and layer 2s in general, we think that they can process a lot of maybe 1,000 transactions per second. And in our mind, it's kind of associated that this was the main reason for their discovery, to increase the throughput of transactions on top of Ethereum. And when it comes to decentralize a sequencer, I think that they will lose some part of their fast throughput. And the question is the following: do you know, when it comes to decentralize a sequencer, what are the approach that they are trying to explore, and what is that they're actually compromising or losing as a trade-off when they're investigating this topic?
Yeah, so first of all, as I said, as an L2, you do not necessarily need to decentralize your sequencer, because as I said, you get consensus and censorship resistance, which are the properties that a validator set gives you from another blockchain. The reason why you would want to do this is because forced transaction mechanisms, for example, are slow. And there are reasons why they're slow. They need to be slower. Like, for example, the fastest way that you can have a forced transaction mechanism from Ethereum goes as fast as Ethereum. And Ethereum produces a block every 12 seconds, which for some of these L2s is way too slow, right? In practice,
Yes.
forced transaction mechanisms are way, way slower. So what if a user wants to have some better like censorship resistance guarantees, or we usually call it real-time censorship resistance, so that I will get my transaction included with very high probability, very fast, like even faster than Ethereum. Some projects are working towards this. There is one that will launch next week, which is called Aztec, that will launch with a decentralized sequencer network. They will have they will have thousands of sequences even. Like, it's something crazy numbers. But the problem is, whenever you add decentralization, there is always a trade-off between speed and security. Because if you have something decentralized, then you need to send messages in the peer-to-peer network, over the internet, and it gets time to reach consensus. So there's always a trade-off between, let's say, security and real-time censorship resistance and speed. So Some
see.
projects decide that one part of the trade-off is better than the other, but at the end of the day, it's subjective.
I see. And when we say about decentralizing the sequencer, are we talking about what happens inside the same sequence, or are we exploring rotating sequencers?
So
Between
some of
blocks.
them are like election-based, which is you have a stake, and then you have a probability of being elected proportional to your stake. This is the same as L1s, like Ethereum. Some of them are much simpler. They're just a round robin, which is like there is a circle of sequencers and they are just chosen in the same circle over and over. But yeah, like there are different strategies. I don't think there's much of a difference as long as the actors that includes the transaction is different, because the guarantee that you want to have is that if someone censors you, you hope that the next one will not.
I see. And last question. Have we seen any of these decentralization attempts going into production in any layer 2?
There are attempts for sure. All of them that I've seen myself, they always have some problems. Like many times when a project wants to decentralize is for like marketing purposes. And this is like the black pill.
I can relate.
It's not because they actually want to provide some properties. It's just because it's cool to say, oh, we're decentralized while our competitor is not. So a lot of times it's kind of fake decentralization. But I know for sure that there are projects that are working towards this. I know Starknet is one of the projects that's working towards this. ZK, as I said, Aztec, which will launch next week, will have like thousands of sequencers live in production, but the throughput of Aztec will be quite low, much lower than Arbitrum and the other big ones that use centralized sequencers. So this is like a fundamental trade-off.
I see. Thank you. Thank you very much. Guys, is there any other question? No. Thank you again very much, Luca, for finding the time and being here with us and kicking off this series of webinars.
Thanks for having me.
Yeah. Thank you so much, Luca. And thanks everyone for attending. Be on the lookout. We'll be announcing future webinars as well as other events. And you can probably find them at our website under the initiative stuff, which I'll share in the chat as well. And of course, in our Discord, if you're not already, we'll be sending out heads up for different things that we're doing, and I'll also drop an invite in the chat as well. But yeah, thanks everyone, and we'll be making the recording available if someone wants to go back to it.
Thank you guys. Bye everyone. Have a good one.